Okay, in this video, we are going to use the properties of Laplace transforms along with a table of some common Laplace transforms to evaluate the Laplace transform of the function 3t squared plus 5e a to the t cosine of bt. So like I said, I don't expect you to memorize all of these Laplace transforms or to verify them every single time. So you can use this like a table of integrals, like a little shortcut for some of these problems. So first thing that we can do is use the linearity properties of the Laplace transform, which is going to allow us to say, first of all, we can break up the sum and then we can pull out constants. Okay, and then we can use our table to evaluate each of the Laplace transforms that are left. So if I want to evaluate the Laplace transform of t squared, well, then it makes sense that we would want to use that power function shortcut. So that means what I'm going to get is 3. And now my value of n is 2 because I have t squared. So I'm going to get 2 factorial all over s to the n again is equal to 2 plus 1. And so for this one, we just would need a domain of s bigger than 0. Since here we're just using the fact that n is equal to 2. And now we can add to that 5 times the Laplace transform of e to the at times the cosine of bt. And for this one, we can use the fact that this is going to equal a shift of the Laplace transform of the cosine of b of t. Okay, so this function f that we're referring to over here, this is actually the Laplace transform of the cosine of b of t, and we just need to shift it now by a units to the right. So now we've got 3 times 2 factorial, that gives us 6 over s cubed, and we're going to add that to 5, and now I'm going to substitute s minus a in for each of the s's in the formula for the Laplace transform of the cosine. So up top I'm going to get s minus a. On the bottom I'm going to get s minus a squared, and then we're going to add to that b squared. And this one is going to be defined as long as s is bigger than a. So altogether, the domain of the first piece was s is bigger than 0, and the second piece is s is bigger than a. So if, for example, we assume that a is a positive number, then altogether we're going to need to require that s is bigger than a in order for both of those terms to converge. So this would be our Laplace transform. And what's important to note here is that I actually didn't integrate anything, just using this table of common Laplace transforms and using some properties of Laplace transforms, I'm able to calculate new Laplace transforms using information about previous ones. So that's really nice here. You wouldn't be expected to integrate this using the definition. And so I just want to kind of summarize the results from the previous slides into this one table. So you can use all of these shortcuts at your discretion. unless you're explicitly asked on homework to, using the definition, derive this formula. If you're not asked that, then you can use all of these Laplace transform shortcuts, and we'll see how they come up in some problems shortly. But I posted a table in Canvas for this, so you can have a printout version of this table that might be useful to have when you're working through the homework on this chapter.